All right, so here we go. So we left off yesterday. Remember, we were talking about, go ahead and click them all the way closed. Get rid of any distractions, please. So we were talking about how do we go about solving polynomial equations, right? Our goal here was we reviewed a bunch of quadratic equations that we already knew how to solve, and we came up with some interesting conclusions. We can make some connections. We found that anytime we have a real zero of a function, right? So if I put a function in standard form, so I set it equal to 0, then the zeros of whatever we have on the other side, right? If they're real numbers, they always correspond to x-intercepts, right? If they are imaginary numbers, on the other hand, they don't correspond to x-intercepts. Right? They're still zeros, but they're not x-intercepts on a graph. We learned some other important stuff. We learned that the fundamental theorem of algebra tells us that if we've got a fifth-degree polynomial, exactly how many zeros are we guaranteed to have? How many complex zeros? 5, for sure. Right? We're guaranteed to have 5. And we looked at a bunch of examples where we saw that. Right? This is a second-degree polynomial. We know that because the highest power of x is a 2, and sure enough, we have 2 zeros, right? Here's a second-degree polynomial. We got 2 zeros. Here's a second-degree polynomial, and we got 2 zeros. They just weren't x-intercepts, but I still got 2 of them, plus or minus 2i, right? But then we got up to one like this, and something strange seemed to happen here, right? We only got one answer. It's a second-degree polynomial, but we only got 1 0. How come? How come? Because this tells us that it has exactly n zeros, but remember it says including multiplicities. Right? Remember, some zeros can count for multiple zeros at once, so they count for more than one. That must be what's going on here. How does this one somehow count? It needs to count for 2, doesn't it? Yes. How does it count for 2? How does that one have a multiplicity of 2? So it actually represents 2 individual solutions. And so the fundamental theorem still works. We got 2, but how? What do we say about that one? Only get one solution, x equals 1, but because the factor that created that, and how do we get that really? We just set the factor x minus 1 equal to 0, right? And solved. And that gave us 1. But the factor that we set equal to 0 there was being squared, right? So therefore it counts as 2. Okay, so it has a multiplicity of 2 because that factor that gave us that answer was squared. And it looked different. Right? Here's the other thing we saw about that. When we look at zeros, at real zeros that have multiplicities of 1, so the factors only show up once, right? Here, this one I got x equals plus or minus 2, the square root of, or plus or minus 2. So each one of those works out to be an x-intercept where the function cuts through the x-axis like a line. Okay? Same thing happened right here. I got 2 separate factors. Each of them was just to the first power, so each had a multiplicity of 1. Once again, the function just cuts through the x-axis like a line cutting through the x-axis. But when we got that one that had a multiplicity of 2, it was different. Look at how that one looks instead. Right? That one doesn't cut through the x-axis. It bounces off of the x-axis like a parabola. Right? And that's because it has a multiplicity of 2. So we can even see that they actually look different. Right? And then the one other thing that we looked at yesterday that was pretty important was when we ended up getting, like here was an example of a second-degree polynomial that had no real zeros, had no x-intercepts. But when we get the imaginary ones, when we get complex solutions that have i's in them, we found out that they always have to come in these complex conjugate pairs. They always come in packets of 2. Right? The packets always look like a plus or minus b times I, where a and b are just numbers. Right? So in this case, A is 1 and B is 2, right? That always happens. And so that's why we said, if we have a 5th degree polynomial, we know we're going to get 5 total complex zeros. But there's only certain ways that can happen, right? Because the imaginary ones have to come in pairs, so we always have to have an even number of imaginary zeros. In this case, we could either have 0 or 2 or 4. If I have no imaginary zeros, then all 5 are going to be real. If I have 2 imaginary zeros, then that leaves 3 of them that are real. And if I have 2 pairs of imaginary for a total of 4, then I only have 1 left over to be a real solution. Okay? All right. So finally we got up to this example here. Okay? Now what do you think we can do with this one? What have we always done in the past with a problem like this? When we've been able to point to a single x, what do we do? Isolate x. That's what we do for quadratics, and it works great for quadratics, right? So let's give it a try here and see if it works for a cubic function. Okay, so what would the 2 steps be in order to solve for x then? Add 8, and then cube root it. Okay, good. So we add 8, and then we cube root it. So what's the cube root of 8? 2. It's not plus or minus 2, it's just 2, right? Negative 2 cubed is not 8, it's negative 8, right? Negative 2 times negative 2 is 4, times negative 2 is negative 8. So it's only one answer this time, it's an 8. Okay, well that seems to make sense. That corresponds to this x-intercept, right? Except, look at that x-intercept. Does that look like, what do you think the multiplicity is of that 0 based on what it does? Does it bounce or do something weird, or does it just cut right through the x-axis like a line? Cuts right through. So that's what we saw with a multiplicity of 1, right? So that only counts as one solution. How many do we know, how many complex zeros do we know that we need to get for this? We gotta get 3. If that one only counts as 1, then we're missing 2. Where'd they go, right? Okay, it turns out that when you isolate x in a function that's bigger than quadratic, it really doesn't work that well. You can get the real solutions that way, but you can't get the hidden imaginary solutions like you can with the quadratic. So we have to do something different, something totally different that we haven't talked about yet. We have to use a factoring pattern, okay? And so let's look at, there's going to be 4 factoring patterns that you just have to know. And these are, I don't really like to have people memorize stuff because it's really a low level of learning. But in this case, you know, you're going to forget it, probably, I would guess, but you still have to memorize it because it's like working memory that allows you to do the problems more easily. If you have to stop every time to remember these patterns, it interrupts your train of thought and makes it too hard. There's only 4 of them, you got to know them. The first assignment that's up there, the first 8 problems there's nothing to do except just practice memorizing. That's it. That's it. So it'll be things like it's going to say a squared plus b squared equals, and you're going to write down a squared plus b squared, right? Because there's no pattern for a sum of squares. If it says a squared minus b squared, you're going to write that down, okay? Now, the first 2 are kind of freebies, I would say. A sum of squares, I mean, there's nothing to remember. When I say a sum of squares, I mean something squared plus something squared. It's not going to be an a and a b. It's probably going to look more like, oh, something like this. What if I have, what if we had something like x squared plus 25? Can we factor that? Well, that looks like something squared, which is an x, plus something squared here, which is a what? What squared is 25? Okay, so that's just fitting the pattern where a is equal to x and b is equal to 5. And then we just follow that pattern. But the thing is, there's really no pattern to follow, right? The sum of squares does not factor, okay? Now, a difference of squares, if I have something of the form a squared minus b squared, we've already talked about that a few days ago, but we talked about it in the other direction. We started here. We said, what happens if we multiply 2 conjugates together? Conjugates are just, you know, where the terms are the same, but I'm adding them for one factor and I'm subtracting them for the other. So a plus b and a minus b, or a and b could be anything. But if it fits that pattern, we call those conjugates. If if I multiply conjugates together, we found that we end up getting a difference of squares, a squared minus b squared. And that goes back to, I think, assignment 5.3, I think it was. Okay. So all we're doing now is we're going the opposite direction. If we start off with a difference of squares, something squared minus something else squared, we know that always factors into conjugate factors, a plus b times a minus b. Okay, let's just do a quick example of that. So what if we start off with something like, well, let's just do x squared minus 25. Okay, we got a binomial there. Anytime, and these are always going to apply to binomials, things with two terms, right? That's what we're learning how to solve today, is how do we solve polynomials with two terms. Well, the only pattern that this one could fit is my difference of squares pattern, right? The only thing that could possibly fit is something in the form a squared minus b squared. And I can see that because I've got an x squared minus something. It's the only pattern it could fit. If it fits that pattern, remember, the result is just a plus b times a minus b. Now the question is, can we make it fit that pattern? So here's what you want to do. You want to ask yourself, can I write this as something squared minus something squared? Well, yeah, we already did. What are they? What's being squared there? X. What's being squared there? So now we just follow the pattern, right? X is a and 5 is b, and so we just fill in whatever we get. So we get x, which is a, plus b, which is 5, times x minus b, which is 5, x minus 5. That's our answer. That's factored. Okay, you get the idea? Okay? So we've got those two that are really easy. And then we've got the two that are a little bit harder. We've got the sum of cubes and the difference of cubes. Right? The sum of cubes means if I've got something cubed plus something else cubed, then that's always going to factor using this pattern. Okay, so how do you remember this pattern? Because it looks like a lot of stuff. There's an easy way to remember this. So when you're factoring a sum of cubes or a difference of cubes, first thing you find is that you get these two factors. One of them is going to be a binomial and one of them is going to be a trinomial. So you get a little one and a big one, right? The little one, the terms in the little one are just always going to be a and b every time. First term is a, second term is b. The trinomial, you're going to get three terms. The first term is going to be a squared, the last term is b squared, and the middle term is just a times b. Not 2 times a times b, just a times b. And then you notice what happens with the signs. Whatever the sign is that you're using, if it's a sum of cubes, it's going to be a cubed plus b cubed. If it's a difference of cubes, then that's going to be a minus sign. Whichever sign shows up in the binomial that you start with, you get the same thing in the first binomial factor. Whatever is there is automatically going to be there. Okay? The first sign of the trinomial is always going to be the opposite of that. So if we start off with a positive, that's going to be a minus. And then the last sign, the last operation, is always going to be positive. Okay? So if I want to do, what do you think is going to happen? What if I started off with a cubed minus b cubed? What do you think the result's going to be? Instead of a plus b, that's going to be a minus b. And instead of a squared minus ab, that's going to be a squared plus ab. And that's always plus b cubed, or plus b squared, sorry. So, let's just show that. So there it is, right? There's the difference of cubes. And so those are the two patterns that we use. And now, that's it. There's just those 4 patterns. That's how we solve, that's how we factor a binomial polynomial every time. We're not going to do anything higher than cubes. We're just going to do squares and cubes. But it's just a matter of being able to apply that. So let's just practice a few of these, and then you can work on this on your own. So what about this guy? What if we want to solve this? Let's go back to this equation, the one that we solved before, but we missed 2 zeros. So what am I going to do with that? Take a second and just look at that and decide, what can we do? We can't, but we isolated x and we only got one answer. It didn't work.
Oh, yeah.
right? So that doesn't work. We've got to use a factoring pattern instead. So what's the only factoring pattern that could work there? Could it be like a sum of squares?
No.
That's not going to work. What's the one that's going to work?
The second one.
The last one. Good.
Yeah.
So a difference of cubes. Sum means you're adding, difference means you're subtracting, right? So it's going to be a difference of cubes. Okay, so now you got to tell me what that pattern is. I bet you all know it already. So I got an a cubed minus b cubed. What's that equal? So first of all, before we put any of the signs in, what goes there? A. What goes there? What goes there? A squared. What goes there? AB. Good. What goes there? Okay. What goes there? Minus. What goes there? Well, it always goes there. That's good. Okay. So now the question is, can we turn this into something that looks like a cube minus a cube? Well, what goes there? X. What goes there? Well, but no, I have to write it as something cubed. 2, right? So I get x cubed minus 2 cubed. Now I just follow my pattern. So that's going to give me an x minus 2 times x squared plus x times 2, which we'd say 2x, plus, there you go, right? So it's factored. Now the whole thing is equal to 0, but now I've got it factored, right? And so once I get it factored, then I can set the factors equal to 0 and solve. So here's kind of the trick with that. When I start with, and eventually we'll look at some bigger polynomials, how far do I have to factor them? Well, if the question says factor it completely, you have to factor it until you can't factor it anymore. I'll give you a couple of those. But a much more useful question is one where it says solve. We just want to get the zeros. In that case, I really don't have to factor it sometimes all the way to its smallest factors. Here's the rule. I just have to factor it until I get either linear or quadratic factors. If I get a linear factor, those are super easy to solve. Like, what's the 0 of that one? If I set it equal to 0, positive 2. Those we've done a ton, right? So we get x equals 2 is one answer, right? This guy right here, now you could try to factor that, but one thing you're going to find, and I'll save you some time, when you do these problems, all of those quadratic factors that you get out of these cube patterns, they're what we call irreducible quadratic factors. Which just means don't bother. They're never going to factor. In fact, not only are they never going to factor, they're never going to give you real zeros. They're always going to give you imaginary zeros. Never real ones, right? So don't even try. So in this problem here then that we're currently working on, there's no point in me trying to factor that further. I can't do it, but I can always get the zeros that come with that, because if I set it equal to 0, it's just a quadratic equation, right? Okay, so what if I do that? What if I set this one equal to 0? I set it equal to 0 and solve. We already said we can't factor it, so how would you solve that quadratic equation? What would you do? Now think back. Okay, raise your hand if you know what to do. I just want to get an idea. Okay, raise your hand if you don't know what to do. If you don't know what to do, I'm going to tell you, you just got to work harder at it, because we've done this a bunch of times. What, I mean, seriously, at some point, the steps get a little bigger, and you just got to do it. What do we do if we're like in Unit 2, when we get to a quadratic equation that we can't factor? What do we do? What do we do? Well, we can't though, right? We said this one, there are never going to be magic numbers.
Divide by 2 ways.
There you go. What do we call that?
Quadratic formula.
Quadratic formula. Right? That's always what we're going to do, right? Okay. So we're just gonna plug this into the quadratic formula. We can always do that with any quadratic equation, right? Okay, I mean, it's always gonna be an option for us, but sometimes we can do something easier, right? And we always will take advantage of that when we can.
Yeah.
But if it's got x squareds and x's, so I can't isolate x, and there are no magic numbers, yeah, I can complete the square, but I would just guess that most people don't want to complete the square. Most people want to just use the quadratic formula because it's the same every time, right?
Yeah.
I would guess. Okay, so let's do that. What is the quadratic formula?
X is negative.
So x equals,
Negative b plus or minus square root b squared minus 2ac divided by 2a.
there you go. So you all know it, right? It's just a matter of plugging in a, b, and c into this thing, right? So what do we get then? If we plug into this, what's negative b for us?
Negative 2.
Negative 2, because b is 2, right? So I get negative 2 plus or minus the square root of b squared,
4.
so that's 4, right? 2 squared is 4, minus 4 times 1 times 4.
Negative 16.
So I'm going to minus 16, right? All divided by 2 times a, 2 times 1 is 2.
Yep.
So those are my answers. I just have to simplify that, put them in the right form. So first of all, what do I get in here? If I simplify inside the radical, what's 4 minus 16?
That would be
Negative 12. So this is just going to become the square root of negative 12, right? Okay. Well, what do I do with the negative inside the radical? It becomes an I. Good. How about the square root of 12? What does that simplify to? We could make a little, if we need to, we can just do this. We can just do this. We can say 12 breaks up into what? We can make a factor tree. 4 and 3, and 4 breaks up into 2 and 2. So now remember, couples go out, singles stay in, right? So we get a couple of 2s and a single 3, right? So all this stuff then is just going to become, look what happens. I get negative 2 plus or minus, all this stuff becomes 2 radical 3 I, all divided by 2. Now the only thing we have to do, if you put that in, it's not going to give you full credit because it wants the answers to be written as complex numbers in their regular standard form, right? Where we have a real part plus an imaginary part. So we have to just break up that fraction into 2 parts. So we would get negative 2 over 2 plus or minus 2 radical 3 over 2 times I. And so what do we get? What's negative 2 over 2? Negative 1 plus or minus, well, 2 radical 3 over 2, the 2's cancel, right? So I just get radical 3 I. So there are my other 2 answers. Notice they're a complex conjugate pair. A plus or minus bi. What's A in this case? Negative 1. What's B? Well, square root of 3, right? So I get A plus or minus B times I. I get my complex conjugate pair of imaginary zeros. And I get my 3. There's 2 of them, and there's the other one, right? Okay, you get the idea? Yeah. Okay, let's try that one. Okay, now that's a big number, right? 729. But there's something else I'm going to give you guys a great deal. This is, you got to take this one while I'm willing to do this. I'm going to give you an opportunity to do a really simple memorization test. It's going to count for an Algebra 2 test. What's going to be on the memorization test? Just 2 things. I want you to know the factoring patterns we just talked about, like a cubed plus b cubed. Finish that statement, right? How easy is that? It's like learning a state calculus. No big deal. This is low-level stuff. This is not like hard math stuff. This is low-level stuff. I want you to know what is a plus b squared, like from 5.3, if I expand those out. A squared plus 2ab plus, I'll give you a little sheet on Moodle, PDF that has everything. And then here's the other part I want you to know. I want you to know your squares through 15 and your cubes through 10. Just because it's so, and most of these you already know. Like if we do squares, you can already tell me. 1 squared is what?
1.
What's 2 squared?
4.
3 squared is?
9.
4 squared is? 5 squared?
25.
6 squared is 7 squared. 8 squared is good. 9 squared is 10 squared. 11 squared. Good. So you already know these. 12 squared. 13 squared.
69.
14 squared.
You lost it. You lost it.
Lost you there?
Yeah.
What's 14 squared? It's 196. Okay, so there's probably just 2 of these you don't know. You know everything probably up through 13 squared. And then what's 15 squared? 225 is correct. Okay, so you got to know those, right? How come you have to know those? Just because you use them all the time in life, and so those are ones that are just important to know. Okay, cubes. You don't have to know as many cubes.
We only have to memorize 1 to 15, right?
1 through 15. That's it. That's it. Okay, for the cubes, what's 1 cube? 2 cube. 3 cube. 4 cube. 5 cube. 125. 6 cube. 216. 7 cube. 343. 8 cube. Yeah. 9 cube. And then finally 10 cube.
1,000.
Okay, that's it. Now, what do you notice here, though? You notice that the cubes grow pretty fast, right? They get pretty big numbers. Okay, but you're going to need them on these problems because you got to be able to recognize 729. If you weren't familiar with the cubes, you'd look at that and think, "Geez, that looks weird." I mean, that doesn't look like anything. But now we know that it is. Right now, we know that this is simply this fits our pattern of a cubed plus b cubed, doesn't it?
Yep.
Right? It fits the pattern of something cubed plus something cubed. Well, there's an x and there's a 9. And we follow the pattern. No big deal, right? Okay, how about one like that? Okay, we're going to solve that. What do we have to do first? Well, okay, 54 won't go evenly into 2,000 though, but it's not a bad idea. But before we even think about that, maybe there's something else you always want to do with any equation. Say it again. Make it equal to 0. Very good. So let's put it into standard form and set it equal to 0. Okay. Now there's the part where we want to see if we can undistribute something. And you don't have to get it the first time. You know, you can do this several times until you get everything out that you can. But what's one thing that we could obviously divide both of those by? 2, right? 2. So we could factor out a 2. What are we left with if we factor out a 2? Not 28. Close. 27 x cubed minus 1,000 equals 0. Okay, now, if this problem said factor completely, Ian, I think you ought to close that up. I think if you're missing this, there's almost no chance you're going to get this at all. So, if this problem said factor this completely, write it in factored form, you'd have to leave that 2 out there. Because when you're all done, ultimately your answer has to be an answer where if I multiplied it together, I get right back where I started, right?
Right.
Okay, so, but it doesn't say that. We're just solving an equation, right? What this really says in this case, I didn't write the words down, but it says solve. Find all complex zeros, or find all complex solutions, right? So then, we could get rid of that 2. I can divide both sides by 2 and make the equation easier, right? Now what I can't do is I can't divide both sides by a variable. That doesn't work, right? Like if I try to take something like, how about this one? What if I have x squared minus 2x equals 0? I could factor out an x, right? And get x minus 2 equals 0. Agreed? So what are my two solutions to this one? Either, what? I've got it factored. If I set that factor equal to 0, what's the value of x? 0, yeah. So either I get x equals 0 or x equals 2, positive 2, right? If I set that equal to 0 and solve. Okay, so I get two solutions to this. But what if somebody tried to divide each side through by x here to get rid of that? So that's just going to be 0 on this side. I would have lost one of my solutions and I would have gotten it wrong, right? You cannot divide by a variable, right? Bad idea. But you can right, so you can't do that. But you can divide each side by 2. What's 0 divided by 2? 0. So I can just get rid of that, right? So I could have even, if I wanted to, I didn't even have to think about this as factoring. If I had wanted to, I could have even, oops, I could have even done this, right? I could have even just said, I know that 2 divides into both of those, so why don't I just divide each side through by 2? Either way, I'm going to get the answer 27x cubed minus 1,000 equals 0, right? Okay, so now we got that thing simplified. There's nothing else I can undistribute or divide both sides by, right? What's the only pattern that we could use to solve that binomial equation? It's the only one that could potentially fit. The last one. So what is that called? It's not a sum, it's a difference. Difference of cubes. Difference of cubes. So can I write it as something cubed minus something cubed? Could I do that? What would this something be? 10. Okay, now what about this one? This is the one that's a little bit tougher. It's going to be a 3x, right? Because I've got to cube the 3 and cube the x. And then all we have to do is just follow our pattern. So let's write the pattern down. A cubed minus b cubed equals what? A minus b, good. No, last one's always plus. Plus b squared. Okay, so now all we got to do is just fill that stuff out. We're going to fill in the blanks with what our a and our b are. So I'm going to get this. So what's a going to be here? 3x. Good. What's b? 10. Okay, here's the one part that's kind of tricky. The one part that's kind of tricky. What do we get? What is a squared? A is what? 3x. So I have to square out the whole 3x. See what I'm saying? Yeah. And then plus AB is easy. What's 3x times 10? Heard it? 30x. Plus 10 squared? 100. Okay? But I have to, that's the part I have to be careful with, right? So I end up with 3x minus 10. What is 3x quantity squared if I square the whole thing? I got to square the 3 and square the x, right? By my properties of exponents. So 9x squared plus my 30x plus my 100. And now all I have to do, I've got the factors down to where they're quadratic or smaller or linear. Set them equal to 0 and solve. So if I set 3x minus 10 equal to 0, what are the two steps to solve for x?
Isolate.
And what do I do? Add 10, divide by 3. So would you agree I'm just going to get 10 on the top and 3 on the bottom, right?
Yes.
When I do that. So there's my real solution. How about these guys? Now this is a quadratic formula thing, right? So I'm going to have to get x equals negative b, so that's negative 30, plus or minus the square root of 30 squared, that's 900, minus, okay, how about this one? 4 times 9 times 100. Well, 4 times 100 is 400. Times 9 would be 3,600. Okay, all divided by 2 times a divided by 18, right? So we can simplify that then. That's going to give me, if I break it up into separate parts, I'm going to get negative 30 over 18 plus or minus the square root of 900 minus 3600 is negative 2700. Okay? Over 18. So 2700, well 2700 is just 27 times 100. So if I wanted to like make a factoring table out of that, I could turn that into 100 times 27. What's 100 break up into? Well, how about 10 and 10? So I get a couple of 10s. 27 is going to break up into 3 times 9. So I get a couple of 10s and a couple of 3s and a single 3. So that's just going to give me 30 times the square root of 3 over 18, and the negative becomes an I. Right? And then I can just reduce those fractions, and I got all three. Okay? All right. You're good.